Section 0 of Climatic Changes, Their Nature and Causes by Ellsworth Huntington. This is a LibriVox recording. All LibriVox recordings in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Leon Harvey. Climatic Changes, Their Nature and Causes. Published on the foundation established in memory of Theodore L. Glasgow. Climatic Changes, Their Nature and Causes by Ellsworth Huntington, Research Associate in Geography in Yale University, and Stephen Sargent Vishner, Associate Professor of Geology in Indiana University. The Theodore L. Glasgow Memorial Publication Fund. The present volume is the fifth work published by the Yale University Press on the Theodore L. Glasgow Memorial Publication Fund. This foundation was established September 17, 1918, by an anonymous gift to Yale University in memory of Flight Sub-Lieutenant Theodore L. Glasgow, R.N. He was born in Montreal, Canada, and was educated at the University of Toronto schools and at the Royal Military College, Kingston. In August 1916 he entered the Royal Naval Air Service, and in July 1917 went to France with the 10th Squadron attached to the 22nd Wing of the Royal Flying Corps. A month later, August 19, 1917, he was killed in action on the Ypres front. To Thomas Trowder Chamberlain of the University of Chicago, whose clear and masterly discussion of the great problems of terrestrial evolution has been one of the most inspiring factors in the writing of this book. There is a toy which I have heard, and I would not have it given over, but waited upon a little. They say it is observed in the Low Countries, I know not in what part, that every 35 years the same kind and suit of years and weathers comes about again, as great frosts, great wet, great droughts, warm winters, summers with little heat, and the like, and they call it the prime. It is a thing I do the rather mention, because, computing backwards, I have found some concurrence. Francis Bacon. Preface. Unity is perhaps the keynote of modern science. This means unity in time, for the present is but the outgrowth of the past, and the future of the present. It means unity of process, for there seems to be no sharp dividing line between organic and inorganic, physical and mental and spiritual, and the unity of modern science means also a growing tendency toward cooperation, so that by working together scientists discover much that would else have remained hid. This book illustrates the modern trend toward unity in all of these ways. First, it is a companion volume to Earth and Sun. That volume is a discussion of the causes of weather, but a consideration of the weather of the present almost inevitably leads to a study of the climate of the past. Hence the two books were written originally as one, and were only separated from considerations of convenience. Second, the unity of nature is so great that when a subject such as climatic changes is considered, it is almost impossible to avoid other subjects, such as the movements of the Earth's crust. Hence this book not only discusses climatic changes, but considers the causes of earthquakes and attempts to show how climatic changes may be related to great geological revolutions in the form, location, and altitude of the lands. Thus the book has a direct bearing on all the main physical factors which have molded the evolution of organic life, including man. In the third place, this volume illustrates the unity of modern science, because it is preeminently a cooperative product. Not only have the two authors shared in its production, but several of the Yale faculty have also cooperated. From the geological standpoint, Professor Charles Schuchert has read the entire manuscript in its final form, as well as parts at various stages. He is helped not only by criticisms, suggestions, and facts, but by paragraphs ready for the printer. In the same way, in the domain of physics, Professor Lee Page has repeatedly taken time to assist, and either in writing or by word of mouth has contributed many pages. In astronomy, the same cordial cooperation has come with equal readiness from Professor Frank Schlesinger. Professors Schuchert, Schlesinger, and Page have contributed so materially that they are almost co-authors of this volume. In mathematics, Professor Ernest W. Brown has been similarly helpful, having read and criticized the entire book. In certain chemical problems, Professor Harry W. Foote has been our main reliance. The advice and suggestions of these men have frequently prevented errors, and have again and again started new and profitable lines of thought. If we have made mistakes, it has been because we have not profited sufficiently by their cooperation. If the main hypothesis of this book proves sound, it is largely because it has been built up in constant consultation with men who look on the problem from different points of vision. Our appreciation of their generous and unstinted cooperation is much deeper than would appear from this brief paragraph. Outside the Yale faculty, we received equally cordial assistance. Professor T.C. Chamberlain of the University of Chicago, to whom, with his permission, we take great pleasure in dedicating this volume, has read the entire proof and has made many helpful suggestions. We cannot speak too warmly of our appreciation not only of this, but of the way his work has served for years as an inspiration in the preliminary work of gathering data for this volume. Professor Harlow Shapley of Harvard University has contributed materially to the chapter on the Sun and its journey through space. Professor Andrew E. Douglas of the University of Arizona has put at our disposal some of his unpublished results. Professors S. B. Woodworth and Reginald A. Daly, and Mr. Robert W. Sales of Harvard, and Professor Henry F. Reed of Johns Hopkins have suggested new facts and sources of information. Professor E. R. Cummins of Indiana University has critically read the entire proof. Conversations with Professor John P. Bowalda of the University of California while he was teaching at Yale make him another real contributor, and Mr. Wayland Williams has contributed the interesting quotation from Bacon on page 10 of this book. Miss Edith S. Russell has taken great pains in preparing the manuscript and in suggesting many changes that make for clearness. Many others have also helped, but it is impossible to make due acknowledgment, because such contributions have become so thoroughly a part of the mental background of the book that their source is no longer distinct in the minds of the authors. The division of labour between the two authors has not followed any set rules. Both have had a hand in all parts of the book. The main draft of chapters 7, 8, 9, 11, and 13 was written by the junior author. His contributions are also especially numerous in chapters 10 and 15. The rest of the book was written originally by the senior author. End of preface. Section 1 of Climatic Changes, The Nature and Causes, by Ellsworth Huntington. This LibriVox recording is in the public domain. Recorded by Leon Harvey. Chapter 1. The Uniformity of Climate. The role of climate in the life of today suggests its importance in the past and in the future. No human being can escape from the fact that his food, clothing, shelter, recreation, occupation, health, and energy are all profoundly influenced by his climatic surroundings. A change of season brings in its train some alteration in practically every phase of human activity. Animals are influenced by climate even more than man, for they have not developed artificial means of protecting themselves. Even so hardy a creature as a dog becomes notably different with a change of climate. The thick-haired husky of the Eskimos has outwardly little in common with the small and almost hairless canines that grovel underfoot in Mexico. Plants are even more sensitive than animals and men. Scarcely a single species can flourish permanently in regions which differ more than 20 degrees Celsius in average yearly temperature, and for most the limit of successful growth is 10 degrees. So far as we yet know, every living species of plant and animal, including man, thrives best under definite and limited conditions of temperature, humidity, and sunshine, and of the composition and movement of the atmosphere or water in which it lives. Any departure beyond the limit means lessened efficiency, and in the long run a lower rate of reproduction and a tendency toward changes in specific characteristics. Any great departure means suffering or death for the individual and destruction for the species. Since climate has so profound an influence on life today, it has presumably been equally potent at other times. Therefore, few scientific questions are more important than how and why the Earth's climate has varied in the past, and what changes it is likely to undergo in the future. This book sets forth what appear to be the chief reasons for climatic variations during historic and geological times. It assumes their causes which can now be observed in operation, as explained in a companion volume entitled Earth and Sun, and such books as Humphrey's Physics of the Air should be carefully studied before less obvious causes are appealed to. It also assumes that these same causes will continue to operate, and are the basis of all valid predictions as to the weather or climate of the future. In our analysis of climatic variations, we may well begin by inquiring how the Earth's climate has varied during geological history. Such an inquiry discloses three great tendencies, which to the superficial view seem contradictory. All, however, have a similar effect in providing conditions under which organic evolution is able to make progress. The first tendency is toward uniformity, a uniformity so pronounced and of such vast duration as to stagger the imagination. Superposed upon this, there seems to be a tendency toward complexity. During the greater part of the geological history, the Earth's climate appears to have been relatively monotonous, both from place to place and from season to season. And since the Miocene, the rule has been diversity and complexity, a condition highly favorable to organic evolution. Finally, the uniformity of the vast eons of the past and a tendency towards complexity are broken by pulsatory changes, first in one direction and then in another. To our limited human vision, some of the changes, such as glacial periods, seem to be waves of enormous proportions, but compare with the possibilities of the universe, they are merely as the ripples made by a summer zephyr. The uniformity of the Earth's climate throughout the vast stretches of geological time can best be realized by comparing the range of temperature in the Earth during that period with the possible ranges shown in the entire solar system, as may be seen in Table 1. The geological record opens with the Archeozoic era, or Age of Unicellular Life, as it is sometimes called, for the preceding cosmic time has left no record that can yet be read. Practically no geologists now believe that the beginning of the Archeozoic was less than 100 million years ago, and since the discovery of the peculiar properties of radium, many of the best students do not hesitate to say 1 billion or 1.5 billion. Even in the Archeozoic, the rocks testify to a climate seemingly not greatly different than that of the average of geological time. The Earth's surface was then apparently cool enough so that it was covered with oceans, and warm enough so that the water teemed with microscopic life. The air must have been charged with water vapor and with carbon dioxide, for otherwise there seems to be no possible way of explaining the formation of mudstones and sandstones, limestones of vast thickness, carbonaceous shales, graphites, and iron ores. Although the Archeozoic has yielded no generally admitted fossils, yet what seem to be massive algae and sponges have been found in Canada. On the other hand, abundant life is believed to have been present in the oceans, for by no other known means would it be possible to take from the air the vast quantities of carbon that now form carbonaceous shales and graphite. In the next geologic era, the Proterozoic, the researchers of Walcott have shown that besides the marine algae there must have been many other kinds of life. The Proterozoic fossils thus far discovered include not only microscopic radiolarians, such as still form the red ooze of the deepest ocean floors, but the much more significant tubes of annelids or worms. The presence of the annelids, which are relatively high in the scale of organization, is generally taken to mean that more lowly forms of animals, such as coelenterates, and possibly even the mollusca and primitive arthropods, must already have been evolved. That there were many kinds of marine invertebrates living in the later Proterozoic is indicated by the highly varied life and more especially the trilobites found in the oldest Cambrian strata of the next succeeding period. In fact, the Cambrian has sponges, primitive corals, great variety of brachiopods, the beginnings of gastropods, a wonderful array of trilobites, and other lowly forms of arthropods. Since, under the postulate of evolution, the life of that time forms an unbroken sequence with that of the present, and since many of the early forms differ only in minor details from those of today, we infer that the climate was not very different from that of today. The same line of reasoning leads to the conclusion that even in the middle of the Proterozoic, when multicellular marine animals must already have been common, the climate of the Earth has already, for an enormous period, been such that all the lower types of oceanic invertebrates had already evolved. Table 1 is displayed on the following page. The geological timetable. Cosmic time. Formative era. Birth and growth of the Earth. Beginnings of the atmosphere, hydrosphere, continental platforms, oceanic basins, and possibility of life. No known geological record. Geological time. Archeozoic era. Origin of simplest life. Proterozoic era. Age of invertebrate origins, an early and a late ice age, with one or more additional ones indicated. Paleozoic era, age of primitive vertebrate dominance. Cambrian period, first abundance of marine animals and dominance of trilobites. Ordovician period, first known freshwater fishes. Silurian period, first known land plants. Devonian period, first known amphibians. Table Mountain Ice Age. Mississippian period, rise of marine fishes, sharks. Pennsylvanian period, rise of insects and first period of marked coal accumulation. Permian period, rise of reptiles, another great ice age. Mesozoic era, age of reptile dominance. Triassic period, rise of dinosaurs. The period closes with a cool climate. Jurassic period, rise of birds and flying reptiles. Comanchian period, rise of flowering plants and higher insects. Cretaceous period, rise of archaic or primitive mammalia. Cenozoic era, age of mammal dominance. Early Cenozoic or Eocene and Oligocene time, rise of higher mammals. Glaciers in early Eocene of the Laramide Mountains. Late Cenozoic or Miocene and Pliocene time, transformation of ape-like animals into man. Glacial or Pleistocene time, last great ice age. Present time. Psychozoic era, age of man or age of reason, includes the present or recent time estimated to be probably less than 30,000 years. Moreover, they could live in most latitudes, for the indirect evidences of life in the Archeozoic and Proterozoic rocks are widely distributed. Thus it appears that in an almost incredibly early period, perhaps many 100 million years ago, the Earth's climate differed only a little from that of the present. The extreme limits of temperature beyond which the climate of geological times cannot have departed can be approximately determined. Today, the warmest parts of the ocean have an average temperature of about 30 degrees Celsius on the surface. Only a few forms of life live where the average temperature is much higher than this. In deserts, to be sure, some highly organized plants and animals can for a short time endure a temperature as high as 75 degrees Celsius, 167 degrees Fahrenheit. In certain hot springs, some of the lowest unicellular plant forms exist in water which is only a little below the boiling point. More complex forms, however, such as sponges, worms, and all the higher plants and animals, seem to be unable to live either in water or air where the temperature averages about 45 degrees Celsius, 113 degrees Fahrenheit, for any great length of time, and it is doubtful whether they can thrive permanently even at that temperature. The obvious unity of life for hundreds of millions of years and its presence at all times in middle latitudes, so far as we can tell, seem to indicate that since the beginning of marine life, the temperature of the oceans cannot have averaged much above 50 degrees Celsius, even in the warmest portions. This is putting the limit too high rather than too low, but even so the warmest parts of the earth can scarcely have averaged much more than 20 degrees warmer than at present. Turning to the other extreme, we may inquire how much cooler than now the earth's surface may have been since life first appeared. Proterozoic fossils have been found in places where the present average temperature approaches 0 degrees Celsius. If those places should be colder than now by 30 degrees Celsius or more, the drop in temperature at the equator would almost certainly be still greater, and the seas everywhere would be permanently frozen. Thus life would be impossible. Since the contrast between summer and winter, and between the poles and the equator seem generally to have been less in the past than at present, the range through which the mean temperature of the earth as a whole could vary without utterly destroying life was apparently less than would now be the case. These considerations make it fairly certain that for at least several 100 million years, the average temperature of the earth's surface has never varied more than perhaps 30 degrees Celsius above or below the present level. Even this range of 60 degrees Celsius, 108 degrees Fahrenheit, may be double or triple the range that has actually occurred. That the temperature has not passed beyond certain narrow limits, whatever their exact degree, is clear from the fact that, if it had done so, all the higher forms of life would have been destroyed. Certain of the lowest unicellular forms might indeed have persisted, for in dormant they can stand great extremes of dry heat and of cold for a long time. Even so, evolution would have to begin almost anew. The supposition that such a thing has happened is untenable, for there is no hint of any complete break in the record of life during geological times, no sudden disappearance of the higher organisms, followed by a long period with no signs of life other than indirect evidence, such as occurs in the Archaeozoic. A change of 60 degrees Celsius, or even of 20 degrees in the average temperature of the Earth's surface, may seem large when viewed from the limited standpoint of terrestrial experience. Viewed, however, from the standpoint of cosmic evolution, or even of the solar system, it seems a mere trifle. Consider the possibilities. The temperature of empty space is the absolute zero, or negative 273 degrees Celsius. To this temperature all matter must fall, provided it exists long enough, and is not appreciably heated by collisions or by radiation. At the other extreme lies the temperature of the stars. As stars go, our sun is only moderately hot, but the temperature of its surface is calculated to be nearly 7,000 degrees Celsius, while thousands of miles in the interior may rise to 20,000 degrees or 100,000 degrees, or some other equally unknowable and incomprehensible figure. Between the limits of the absolute zero on the one hand, and the interior of a sun or star on the other, there is almost every conceivable possibility of temperature. Today the Earth's surface averages not far from 14 degrees Celsius, or 287 degrees above the absolute zero. Toward the interior, the temperature in mines and deep wells rises about 1 degree Celsius for every 100 meters. At this rate, it would be over 500 degrees Celsius at a depth of 10 miles, and over 5,000 degrees at 100 miles. Let us confine ourselves to surface temperatures, which are all that concern us in discussing climate. It is being calculated by pointing that if a small sphere absorbed and re-radiated all the heat that fell upon it, its temperature at the distance of Mercury from the Sun would average about 210 degrees Celsius. At the distance of Venus, 85 degrees, the Earth, 27 degrees, Mars, negative 30 degrees, Neptune, 219 degrees. A planet much nearer the Sun than is Mercury might be heated to a temperature of 1,000 or even several thousand degrees, while one beyond Neptune would remain almost at absolute zero. It is well within the range of possibility that the temperature of a planet's surface should be anywhere from near minus 273 degrees Celsius up to perhaps 5,000 degrees Celsius or more, although the probability of low temperature is much greater than of high. Thus, throughout the whole vast range of possibilities extending to perhaps 10,000 degrees, the Earth claims only 60 degrees at most, or less than 1%. This may be remarkable, for what is far more remarkable is that the Earth's range of 60 degrees includes what seem to be the two most critical of all possible temperatures, namely the freezing point of water, 0 degrees Celsius, and the temperature where water can dissolve an amount of carbon dioxide equal to its own volume. The most remarkable fact of all is that the Earth has preserved its temperature within these narrow limits for 100 million years, or perchance 1,000 million. To appreciate the extraordinary significance of this last fact, it is necessary to realize how extremely critical are the temperatures from about 0 degrees to 40 degrees centigrade, and how difficult it is to find any good reason for a relatively uniform temperature through hundreds of millions of years. Since the dawn of geological time, the Earth's temperature has apparently always included the range from about the freezing point of water up to the point where protoplasm begins to disintegrate. Henderson, in The Fitness of the Environment, rightly says that water is the most familiar and the most important of all things. In many respects, water and carbon dioxide form the most unique pair of substances in the whole realm of chemistry. Water has a greater tendency than any other known substance to remain within certain narrowly defined limits of temperature. Not only does it have a high specific heat, so that much heat is needed to raise its temperature, but on freezing it gives up more heat than any substance except ammonia, while none of the common liquids approach it in the amount of additional heat required for conversion into vapor after the temperature of vaporization has been reached. Again, water substance, as the physicists call all forms of H2O, is unique in that it not only contracts on melting, but continues to contract until the temperature several degrees above its melting point is reached. That fact has a vast importance in helping to keep the Earth's surface at a uniform temperature. If water were like most liquids, the bottoms of all the oceans and even the entire body of water in most cases would be permanently frozen. Again, as a solvent, there is literally nothing to compare with water. As Henderson puts it, nearly the whole science of chemistry has been built up around water and aqueous solution. One of the most significant evidences of this is the variety of elements whose presence can be detected in seawater. According to Henderson, they include hydrogen, oxygen, nitrogen, carbon, chlorine, sodium, magnesium, sulfur, phosphorus, which are easily detected, and also arsenic, cesium, gold, lithium, rubidium, barium, lead, boron, fluorine, iron, iodine, bromine, potassium, cobalt, copper, manganese, nickel, silver, silicon, zinc, aluminium, calcium, and strontium. Yet in spite of its marvelous power of solution, water is chemically rather inert and relatively stable. It dissolves all these elements and thousands of their compounds, but still remains water and can easily be separated and purified. Another unique property of water is its power of ionizing dissolved substances, a property which makes it possible to produce electric currents in batteries. This leads to an almost infinite array of electrochemical reactions, which play an almost dominant role in the processes of life. Finally, no common liquid except mercury equals water in its power of capillarity. This fact is of enormous moment in biology, most obviously in respect to the soil. Although carbon dioxide is far less familiar than water, it is almost as important. These two simple substances, says Henderson, are the common source of every one of the complicated substances which are produced by living beings, and they are the common end products of the wearing away of all the constituents of protoplasm, and of the destruction of those materials which yield energy to the body. One of the remarkable physical properties of carbon dioxide is its degree of solubility in water. This quality varies enormously in different substances. For example, at ordinary pressures and temperatures, water can absorb only about 5% of its own volume of oxygen, while it can take up about 1,300 times its own volume of ammonia. Now for carbon dioxide, unlike most gases, the volume that can be absorbed by water is nearly the same as the volume of the water. The volumes vary, however, according to temperature, being absolutely the same at a temperature of about 15 degrees Celsius or 59 degrees Fahrenheit, which is close to the ideal temperature for man's physical health and practically the same as the mean temperature of the Earth's surface when all seasons are averaged together. Hence, when water is in contact with air, an equilibrium has been established. The amount of free carbonic acid in a given volume of water is almost exactly equal to the amount in the adjacent air. Unlike oxygen, hydrogen, and nitrogen, carbonic acid enters water freely. Unlike sulfurous oxide ammonia, it escapes freely from water. Thus the waters can never wash carbonic acid completely out of the air, nor can the air keep it from the waters. It is the one substance which thus, in considerable quantities relative to its total amount, everywhere accompanies water. In earth, air, fire, and water alike, these two substances are always associated. Accordingly, if water be the first primary constituent of the environment, carbonic acid is inevitably the second, because of its solubility possessing an equal mobility with water, because of the reservoir of the atmosphere never to be depleted by chemical action in the oceans, lakes, and streams. In truth, so close is the association between these two substances that it is scarcely correct logically to separate them all. Together they make up the real environment, and they never part company. The complementary qualities of carbon dioxide and water are of supreme importance because these two are the only known substances which are able to form a vast series of complex compounds with highly varying chemical formula. No other known compounds can give off or take on atoms without being resolved back into their elements. No others can thus change their form freely without losing their identity. This power of change without destruction is the fundamental chemical characteristic of life, for life demands complexity, change, and growth. In order that water and carbon dioxide may combine to form the compounds on which life is based, the water must be in the liquid form. It must be able to dissolve carbon dioxide freely, and the temperature must not be high enough to break up the highly complex and delicate compounds as soon as they are formed. In other words, the temperature must be above freezing, while it must not rise higher than some rather indefinite point between 50 degrees Celsius and the boiling point, where all water finally turns into vapor. In the whole range of temperature, so far as we know, there is no other interval where any such complex reactions take place. The temperature of the Earth for hundreds of millions of years has remained firmly fixed within these limits. The astonishing quality of the Earth's uniformity of temperature becomes still more apparent when we consider the origin of the Sun's heat. Where that origin is still remains a question of dispute. The old ideas of a burning sun, or of one that is simply losing an original supply of heat derived from some accident, such as collision with another body, were long ago abandoned. The impact of a constant supply of meteors affords an almost equally unsatisfactory explanation. Moulton states that if the Sun was struck by enough meteorites to keep up its heat, the Earth would almost certainly be struck by enough so that it would receive about half of 1% as much heat from them as from the Sun. This is millions of times more heat than is now received from meteors. If the Sun owes its heat to the impact of large bodies at longer intervals, the geological record would show a series of interruptions far more drastic than is actually the case. It has also been supposed that the Sun owes its heat to contraction. If a gaseous body contracts, it becomes warmer. Finally, however, it must become so dense that its rate of contraction diminishes and the process ceases. Under the Sun's present condition of size and density, a radial contraction of 120 feet per year would be enough to supply all the energy now radiated by that body. This seems like a hopeful source of energy, but Kelvin calculated that 20 million years ago it was ineffective, and 10 million years hence it will be equally so. Moreover, if this is the source of heat, the amount of radiation from the Sun would have to vary enormously. 20 million years ago, the Sun would have extended nearly to the Earth's orbit and would have been so tenuous that it would have emitted no more heat than some of the nebulae in space. Some millions of years later, when the Sun's radius was twice as great as at present, that body would have emitted only 1/4 as much heat as now, which would mean that on the Earth's surface the theoretical temperature would have been 200 degrees below the present level. This is utterly out of accord with the uniformity of climate shown by the geological record. In the future, if the Sun's contraction is the only source of heat, the Sun can supply the present amount for only 10 million years, which would mean a change utterly unlike anything of which the geological record holds even the faintest hint. Altogether, the problem of how the Sun can have remained so uniform and how the Earth's atmosphere and other conditions can also have remained so uniform throughout hundreds of millions of years is one of the most puzzling in the whole realm of nature. If appeal is taken to radioactivity and the breaking up of uranium into radium and helium, conditions can be postulated which will give the required amount of energy. Such is also the case if it be supposed that there is some unknown process which may induce an atomic change like radioactivity in bodies which are now supposed to be stable elements. In either case, however, there is as yet no satisfactory explanation of the uniformity of the Earth's climate. 100 million or 1,000 million years ago, the temperature of the Earth's surface was very much the same as now. The Earth had then presumably ceased to emit any great amount of heat. If we may judge from the fact that its surface was cool enough so that great ice sheets could accumulate on low lands within 40 degrees of the equator. The atmosphere was apparently almost like that of today, and was almost certainly not different enough to make up for any great divergence of the Sun from its present condition. We cannot escape the stupendous fact that in those remote times the Sun must have been essentially the same as now, or else that some utterly unknown factor is at work. End of section 1.